Welcome to Tommy's ASMR. Today I'm going to be teaching you something in computer science called breadth first search and something else called depth first search. So just as some background, I'm a computer science student in college, going to my junior year. And these are two search algorithms that I think are really, really cool, and I just wanted to show them to you today. Okay, so first, let's get into something called a graph. Now, a graph is a structure, a data structure, made up of nodes or vertices and edges, which are connections between those nodes. Some of these some of these graphs are directed, while others might be undirected. I will absolutely provide more information and research resources on these graphs in the description, and I'll make sure that whoever wants to look more into it will have the opportunity to look more into it. So here are some examples of graphs. As you can see, the graphs themselves, they have, like I said, we're looking at some of these are the nodes, and then some of them are have arrows on them, which make them directed. Now, what is a tree? A tree is a special type of graph that has special properties. In a tree, there's a path between any two nodes or vertices. There are no cycles, meaning that you cannot go back to another node by following the edges. It also has a single starting point, and every node has exactly one parent. Just like graphs, there are many types of trees, and I'm going to do my best to show you how breadth first search, otherwise known as BFS, and depth first search work on these trees. Just like with the graphs, I'm going to link some information in the description in case you're interested in anything about regarding like the trees themselves, because trees are a type of graph. Now, why would we want to search a tree? Like, what are the applications? They allow us to look up data very, very quickly and to visit every single piece of data, discovering the paths of data. An example of this could be file systems, organizational systems, or a system where somebody will make decisions based on data. The reason I want to show you how BFS and DFS work on trees before I do it on graphs is because it's much easier to learn when you're looking at a tree first. That's what I find. I find it much, much easier. Again, with all these different types of trees and graphs, although the attributes and properties of these structures may differ, we can understand the ways in which BFS and DFS search them. Let's start with BFS. BFS means breadth first search. It is one of the two algorithms that we're going to be covering today, the other one being DFS. What this algorithm does is it explores these nodes or vertices in a level by level order. What this algorithm does is that it kind of acts like a cautious explorer. Like, you want to see all the options before you make a decision, right? And in the BFS algorithm, we mark every node that we have visited and added it to something called a queue. A queue is a data structure that where it's like a list, right? A as you can see by the red circle, that's what's in the queue. And this marks A as a visited node. Next, we dequeue A, and we remove it from the queue, and we add its neighbors B and C to the queue. As you can see, the visited array shows A, B, and C, everything that we visited, but the queue no longer has A. Our final output, which technically isn't really final just yet, it only has A because it's the only thing that's been dequeued. Next, we dequeue B, and we add its neighbors D and F. Notice that we add B to the output because all of its children have been visited.
Hold on, I made a spelling error.
All of its children have been visited. Now inside the queue, we have C, D, and F. A, B, C, D, and F are in the visited queue, and since we dequeued B, it is in the final output. Next, we dequeue C and add the neighbors E and G. C is in our final output, and our queue is D, F, E, and G. Next, we dequeue D. It has no neighbors or children, so we just move on. F, E, and G. And our visited is A, B, C, D, F, E, and G. And our final output is A, B, C, D. Next, we dequeue F. It has no neighbors or children, so we just move on. And then for E, and then G. And it is now complete. We have finished with our BFS on a tree. Now we're going to look at something called an undirected graph. Now notice in the undirected graph we have no arrows. That shows that it's undirected and there's no guidance or anything like that on which ways can be traversed. That's important if you're looking at more advanced graphs where it is being able to know which direction based on like other circumstances or something crazy. It's a rabbit hole, so that's part of the reason why I'll be able to link those sources down in the description. So on a graph, we start at node A. Node A is added to the queue. Same deal. And then we dequeue A and add in the neighbors B and C. Fairly similar now. However, we were just at B, but C and B is an edge. Now, that might be strange because wouldn't B have to look at C, which is already in the queue? Well, no. Different from our tree, B and C, the neighbors of A are connected, but A and C are already visited, and C is still in the queue because when we dequeued A, we put C in there. Now this is why having a queue is important, because we know that the first element in the queue is what we're going to dequeue next. So we dequeue C, and since C has no new neighbors, we don't do anything. And so this continues on where we dequeue D, and there's only E left in the queue, and then we dequeue and get G and F. Dequeuing G, no new neighbors, and the queue is now empty. And that's it. That's it for BFS on a graph and BFS as a whole. Let's take a look at DFS, otherwise known as depth first search. doesn't really work in this case. So now let's do DFS on a tree. We start at node A, and this makes A the visited node. Next we pop A, and we add. I don't want to say pop into the mic too much. I think that might cause too many peaks. But we do pop A, and we add neighbors B and C. Since C was the latest node to get added to the stack, then we pop C and add the neighbors E and G. So now our stack is B, E, and G. Now we pop G, and since there are no neighbors to add, we then just backtrack. And now watch this. We pop E. Notice how E was right next to G. And then, because B was the only thing in the stack, we pop B. And our stack is D and F. Next we pop F. And because only D is in the stack, we then pop D, and we have no new neighbors. So now we've done DFS on a tree. Let's try it on the undirected graph. We start at node A, add A to the stack. We pop A and add the neighbors B and C. And in the same scenario, we pop C, and since C has no new neighbors, we don't add anything. B is still at the stack from when A is popped. Next we pop B and add the neighbors D and E. And then after popping E, we add the neighbors G and F. And then we pop F. No new neighbors. Let's backtrack. Then we pop G. And now only D is in the stack. And then we pop it and we're done. Now I want you to notice, right? Different curriculums or different courses or different classes, different professors may tell you the order that they want you to add nodes when multiple nodes are added to the stack. For example, when we're asked to pop B and it has the neighbors or children, which are the same thing, C and D, right? And we add them into the array as C, comma D. We can also do D, comma C. There can be multiple solutions. Usually, they ask you to do it in alphabetical or numerical order. Now, to compare BFS and DFS, some